All right, welcome all. It's a pleasure to have our guest lecturer today, Letiția Pârcălăbescu. Letiția studied physics for her bachelor and her master's, went on to do her PhD in computer linguistics, and is now working with Aleph Alpha. And she is an expert in large language models, and you are just a tiny part of her audience. I already told you she has this hugely successful YouTube channel, and it is hugely successful because she's given very clear and insightful presentations on the latest and greatest in that field. And so it's really very wonderful that you are with us this morning. Letiția, many thanks for coming. Please welcome Letiția.
Good morning, everyone. Thanks a lot for the very kind introduction. And I'm very happy to be here today because, yes, indeed, I studied physics. And in this very room, on these very seats, I had my hydrodynamics lecture, my statistical physics lecture, astrophysics 1 and 2. And now it's good to be back for a short visit to talk about the topic that excites me the most, namely large language models. So, yeah, today we will discuss about the fundamentals of large language models. And, you know, the most important things to know about large language models is the transformer architecture, because transformers have been the backbone of large language models since 2017. Before 2017, there were language models. They were just not so successful, and they were not transformer-based. And, but it was just the advancements and, let's say, the tricks that were established after 2020 that made transformer language models so good that they reached the caliber of ChatGPT. And once they reached the level of ChatGPT, they made it into press headlines and brought them into everybody's hands. Do I even need to ask who doesn't use ChatGPT? Who doesn't use ChatGPT? I want hands raised. Okay, so it seems like everybody uses ChatGPT. I think then we don't require any further motivation into why it is important to learn about language models if everybody uses ChatGPT and is impressed by that model. So yeah, let's discuss the backbone architecture of ChatGPT or any other language model out there that is performant today, namely the transformer. We are doing here deep learning, so it's maybe not a surprise that a transformer is a deep learning architecture, as it's composed of multiple layers called transformer layers. And very specific to the transformer is that these layers are identical. This is a little bit unlike other architectures that you may know about, like convolutional neural networks usually have a different number of parameters and neuron in each layer. They're all convolutional layers somehow, but they differ in hyperparameters. For the transformer layer, it's quite specific that they have the same number of parameters and the same hyperparameters for each layer, so you could say the transformer layers are identical. And we're doing deep learning, so the idea is to start with some representations of our input and get better representations of that inputs in these output vectors, such that the solution to our task becomes obvious. I'll get into more details about what that means, but for a transformer, these input representations are vectors, sequences of vectors. And in general, in deep learning, the input to deep learning architectures is either vectors or these higher dimensional vectors named matrices or these higher dimensional matrices named tensors. For transformers, it's quite simple because they're all vectors. And we produce, after applying all these transformer layers, better representations, better vectors, where the solution of the problem that we have at hand is more obvious. So if I talk about obvious solutions, let's first define a task, like what are we even trying to solve here? Well, we're talking about large language models, so maybe it's a good idea to say we want to continue this text that I just started writing here, attention works. And of course, in general, you could choose any word, but I want to keep the decision and the task as simple as possible, such that the decision is a binary decision. So I will just ask, our task for this transformer is, please decide whether the word well is a good continuation of this sentence. In other words, can I say attention works well? Yes or no? Is that a plausible sentence? Or in other words, I'm asking whether I can replace this weird CLS token in orange, the CLS vector, with well, and that would be a valid sentence. That's the question. And the idea is that I'm applying all these transformer layers such that the representations are obviously giving me the solution for this task. What does this mean? Well, this kind of means that we have a linearly separable representation space, that the CLS tokens representation for all sentences that can end in well are on one side of the representation space, and all the so the representation of the CLS token for all the sentences that do not end well, they're on the other side of the representation space. Here, I've taken the liberty of drawing this representation space, which is obviously 4-dimensional into 2 dimensions. I didn't do any dimensionality reduction. I just, thought it's very hard to visualize 4 dimensions. I chose 2 dimensions, but imagine this is a 4-dimensional space, and this line, which in 2 dimensions is a line to do linear separation, it's a hyperplane in more dimensions. And usually, I mean, if you're even asking what is the dimension of these vectors, usually 4 is a complete understatement. Usually these vectors are 512, 768, 1024, 2048, or whatever dimensions. It basically depends on how many GPUs you have and how much can you fit on your GPUs, how this dimensionality is. And of course, the higher the dimensionality, the better the model is. But yeah, so what we're trying to do is to get representations that are better by applying these transformer layers. And the idea is that we expect the representations for the CLS token before that we apply this transformer layer to not have this obvious solution in them. So the representations for sentences that end well and do not end well are not linearly separable. The idea is to have here at the end a representation where we can just train a linear layer. Because by training a linear layer, we basically find via stochastic gradient descent where to position exactly this line, but the representation should be good enough that they're even separable by a line in the first place. That's why we are applying all these transformer layers in the first place. Okay. So transformers are composed of multiple transformer layers. So what does each transformer layer do? Well, basically, it's a very dimensionality preserving transformation. We start with L d-dimensional vectors and produce L d-dimensional vectors, just other L d-dimensional vectors that hopefully should be better to give us the representation such that the solution becomes obvious to our task. Yeah, so this is a little bit, again, unlike many other architecture, which are less dimensionality preserving than this one. But before I go into details into explaining what exactly are the components of this transformer layer, I have to first unravel the mystery of how do we even represent text as vectors. Yeah, because as I was saying, deep learning needs vectors or these multi-dimensional vectors, however, but transformers need these vectors. And it's not clear how to come from language to vectors. So how to do it? Well, there is a naive idea to go about it. And let's see how far we get with this naive idea until we have to fix it somehow. So the naive idea is to basically have a huge corpus of text. And on this huge corpus of text, we want to train our transformer. And in this huge corpus of text, we look at all unique words that have been used and make a list out of them, and we somehow index that list such that we can really make a dictionary. And it doesn't depend on in which order we have these words. It's just that every word should have a unique identifier. And then to each unique identifier, we initialize a so-called word embedding. This word embedding is a d-dimensional vector, which will, and the scope of this vector is to basically capture the semantics of the word. So how to capture the semantics, or how to initialize such a vector to capture the semantics of the word? You don't need to care about that. You just initialize these vectors randomly. They should just be unique. So mother, every time you see mother, it should get always the same vector for mother. And attention, the word attention should get another vector. So as long as you have initialized unique random vectors, you're fine. You will let the transformer figure out for itself what these vectors should be. So every time you will see the word mother during training, you will update the corresponding word embedding for mother. And the same holds for all the other words. Yeah, so that's a cool part of deep learning. You don't have to care about initializing representation too much. You just let the model figure out for itself what are better representations such that the solution becomes obvious. But now we run into a problem. Namely, we had this huge training corpus. We had, let's say, the entire internet where we looked at all possible words that are in there, but yet there will be always the case that there will be at test time another word that nobody has taught before during training. Here I have a simple example of, let's say, there's variations of how you could say a word. I can say mom instead of mother, and the problem, the hugest problem with text is typos. Yeah, I can, for example, spill some coffee on my keyboard and then attention will look like this. And this is a problem because now every word that was not seen during training doesn't have a good word embedding. It has to map to a certain unknown token, which we define. But this means that every unknown word will map to the same word. They will not be distinguishable. And this is a problem because we want to somehow deal with words that weren't in our vocabulary somehow. So how to do that? Well, by tokenization. Tokenization is basically the solution to this problem by composing the vocabulary not of words, but out of subwords. And the idea is still to keep very, very common words as words in this subword vocabulary, but to split the rarer words into multiple subwords, and this, of course, will become sometimes unintuitive. So here, for the common words, the model will really see the words. For the more uncommon words, they will see these broken down words, which look very unhuman to us. But yes, this is how the model will process its input. And in the worst-case scenario, each character will become such a subword. Yeah, this is the worst case scenario for a really bad typo, for example. But yeah, here is the idea that we split mom into MOM, for example, and M gets the 26 ID, and then O gets another ID, M gets again the same ID as the previous M, and then we have 3 vectors instead of just 1 to represent this, this word, because we had to split it into 3 subtokens, and each subtoken, so the token M, will get updated every time we see the token M alone, so the ID 26 somewhere in our training data. Okay, if you have any questions, you feel free to interrupt me. I'll also have time for questions in between chapters. But yeah, so now the natural question that arises is how to split this into subwords, like how to determine the subwords. And there are many tokenizers. So there's many tokenizers one could have as an example, but I chose here the byte pair encoding tokenizer, which is one of the most common ways to do tokenization. And these tokenizers undergoes a so-called training phase. This training phase is very different from the transformer training. So this is something which happens not even necessarily with a transformer, way before you actually train a deep neural network with this. To train a tokenizer just means that you determine basically a target vocabulary size. So let's say we aim at having a vocabulary size of 60,000 tokens. This is a hyperparameter I just invented, and this is, you know, a good hyperparameter for most purposes. But we set this target vocabulary size. It could be 23,000. It could be anything else. I just say 60,000. And we start with a set of characters as individual tokens. Yeah, and then we progressively look at our data and the frequencies of these subwords, these characters occurring together, and merge the most frequent pairs occurring together in the training data, and we store the resulting subword and the merging rule, and we do this iteratively until the target vocabulary size was reached. Yeah, and this is the so-called training phase, and of course it's an exhaustive search that can become very computationally intensive, and it is. So if you want to burn CPUs, this is the task to do it. GPUs, it's for transformers to burn. Okay, so after we have trained this tokenizer, we are ready to use it. How to pre-process text, to tokenize text for further transformer training. So what we do is basically we split, the BPE algorithm splits all words into individual characters and applies the lowest ranking rule until no further rule applies, and then we have tokenized our text. And this is just one of the example of tokenizers. There's many other tokenizers. For a while, quite interesting is that tokenizer research was kind of still not much was happening on new tokenizers, but this year the tokenizer research exploded, so there's a lot to read at iClear if you're interested. Okay. So yeah, this is how we get from words to these subwords, or also called tokens, and each token gets a unique token ID, and each unique token ID gets a unique word. And that's how we can represent then this text as vectors, and here basically I've hidden that there's a whole tokenization phase that happens. Good, so after we have clarified this, we are ready to go into the details of how to compose a transformer layer. And don't worry, we will compose the transformer layers from components you already are familiar with from this lecture. We can start by applying the simplest neural network you can think of, the multi-layer perceptron, also called feed-forward neural network, also called vanilla neural network, also called fully connected neural networks. Yes, there's 4 names for exactly the same thing. So it's the simplest thing you can imagine. It's a fully connected network, and the usual architecture of this MLP in transformers is the following. You take the input dimensionality, double it via a fully connected layer with the Jello activation function, then downsize it again to the original dimension with again a fully connected layer. And the very important thing to know about this here is that the same weights you're applying to one token, you're applying to every other token. It's not different weights, it's not a different feed-forward network, it's the same exact matrix multiplications that you do for this token that you do for every other token. And this concept of weight sharing is familiar to you from CNNs. CNNs also have some weight sharing. And the coolest part, about this weight sharing in transformers, and that we process these tokens in parallel, is that if we process an entire sequence of text in parallel, we can get much farther with reading the entire internet than we could before. So people will tell you attention is all you need, transformers are cool, and so on. But the reason why transformers are so much more successful than architecture before them as language models is that while recurrent neural networks, which were the language model paradigm before transformers, had to read token after token after token after token. So they had to wait for the processing of the previous token to finish to even start with the processing of the next token. This is very slow, this sequential processing. And now with the transformer, you could suddenly read Wikipedia in a couple of days. With RNNs, you had a couple of months you needed for reading entire Wikipedia. And people said, oh, I read Wikipedia in 3 days, I can then go on to read Reddit and Twitter and the entire internet. And with more data, with more things you have read about language and about the world, of course, the better these neural networks will become. So this is basically the breakthrough that transformers were representing, this parallelization. Which meant that we could speed up a lot of how much text we could process, thus how many capabilities the models could learn. Okay, this is the cool thing about the feed-forward neural network. Could we leave it at this? Could we just call it a day and say this is a transformer? Or maybe something's missing? What's the problem with the current architecture that we have on the slide? What do you think? Yeah? Exactly. There's no information flow, no connection between the tokens. So I was motivating this entire, transformer layer processing that we have some, let's say, stupid representations, and we want to get better representations. But how is the poor works token to understand about the company it keeps if we don't have information flow between the tokens? And because maybe you know that that words are very much defined by the company they keep. A word on itself has a meaning, of course, but that meaning can change very much depending on the company that word keeps. So we somehow need a mechanism to get this information flow between tokens going. Can you think of a component that you already know about from this lecture to add here to enable this communication? Yes? Attention is all you need, exactly. So we can add attention, and the thing is with, so let's start slow. Attention is all you need, great. Attention will enable us communication between the tokens, because what does attention do? Attention is a glorified data-dependent weighted averaging. Because to compute how much I want So to compute the representation of this token after the self-attention layer, basically the multiplication by query and key will give me, and the softmax of course, will give me a percentage of how much of the value of that token I want to preserve to get the output information. So basically, you can imagine that this 80% is a data determined value, number that I determined from data that will tell me that I want to keep, to compute a new representation of attention, the word attention. I need to keep 80% of the value of this token and 15% of the value of the other token and so on. And this is a data dependent weighted averaging that basically is just doing that. It enables communication, information mixing between tokens. And there's this paper title called, attention is all you need, and people kind of believe it. I don't believe it as much. Why? Because if you actually look into the transformer architecture, the number of learnable parameters of self-attention is 1/3 of the entire transformer layer. The bulk of the computation and the number of parameters actually is in this feedforward layer that doesn't even, do any attention or something. So parameter-wise, attention is not necessarily what you need. If you want to look at where the model stores information, it's actually in the feed-forward neural network. So if you do interpretability, people have looked at attention for a long time in interpretability, but then realized, oh, the knowledge is actually very much ongoing here. This is just a way of saying I want to route information and focus on some tokens. And another reason for why attention is not all you need is that it's so easy to replace attention with anything else. There's an entire series of papers replacing self-attention, and self-attention just, gives you the edge in performance if your sequence length is not too high. But if your sequence length is very high, you again have to think about alternatives and how to linearize attention and so on. So yeah, I would say take this with a grain of salt. Attention is not all you need. I think it's this parallel processing via feed-forward networks and the good token mixing that you need. Good. So now we have cleared this up. And we have to still discuss about something because this architecture, this transformer architecture is not complete. Because let's look at the representation of this CLS token. And we didn't discuss what that is yet. This will come later in the slides. The idea is for the CLS token, to have a better representation at the end. But the question is, does the representation of the CLS token even change at all if we input works attention versus attention works? Would the values of this vector be any different if we have attention works versus works attention? Yes or no? Who says yes, they will be different? One hand. Who says no? Many hands. Okay, why not? So you already know the answer. Why would this not change? Yeah? Yeah. Exactly. So I repeat this a little bit more loud. Exactly, that's a perfect answer. Basically, we're having self-attention, which in the end is just a weighted sum, and sums are commutative. Then we have this feed-forward neural network that processes each token independently. So no, the processing of the CLS will not change depending on what the other tokens did. So it's very permutation invariant. And it's a bad thing if in our language input, order matters. And usually there are a lot of modalities. There's a lot of types of inputs where order matters. In language, it's very different if you mess up words or not. And in images, you cannot just shuffle around pixels in the image and say it's still a cat. It's not. Yeah, if you usually shuffle pixels in an image. So we somehow need a mechanism to break this symmetry that a transformer has. We don't like that it's permutation invariant for this language task. Of course, you can imagine that there are data scenarios where this symmetry is actually a plus. But in the case of language, we want to break the symmetry. So we need a kind of a way to say, this is the first token. This is the second token. There's a third token. And this is what happens through so-called position embeddings. Position embeddings you can imagine as an additional vector that we can add to the semantic representation of the word embeddings or concatenate to it. And it acts a little bit like a house number. So if this is the street address, this is the house number. Here we say we're on the Philosophenweg, here we say we're on the Philosophenweg 12. And this is basically the role of positional embeddings, because even if you give here another token instead of attention, you say, for example, works, the semantic embedding of the token will change according to, you know, the new token that you just inserted, but the position embedding will stay the same, because the position embedding for whatever the first token is always this position embedding. And this is a way to encode this positional information into transformers. And the question then which arises is how to do that. Well, there's many ways to do that, and the Attention is All You Need paper that introduced the transformer had this solution. The idea is based on sines and cosine functions that you basically let oscillate over the dimensions here. And why sines and cosines? Well, because sines and cosines are periodic. And the idea of this periodicity is that it would help with generalization to sequence lengths that you never seen during training, or you have seen very rarely during training. Because let's suppose my maximum sentence length in training was 2000, then what happens with our positional embeddings if I go during testing, a user writes a lot to my language model and will go to the 2001 token? Well, it could go out of distribution, but hopefully not, because these sines and cosines are periodic, so values will eventually repeat, and the model will kind of know what to do there. Will not be totally out of distribution. Okay, that's the idea behind sines and cosines, but of course it doesn't work as well as we would like to. And also, what people could ask is, why do we divide here by 10,000? Why do we have here division by the dimensionality of the vector? Why do we choose not 9,999? And the answer is because it works best in experiments, or at least that works best for the Attention is All You Need paper. And yes, if you could exhaustively search with other coefficients and find maybe there's other coefficients that work better, but of course it's hard to do this exhaustive search, so why put a lot of effort and brain power into finding this out if you could just say, let's learn the positional embeddings. Let the data speak for what good positional embeddings are. So in the same way in which here you learn the semantic embeddings of tokens, you can just learn the position embeddings too. And this is a very popular position embedding for transformers that process images, for VITs, vision transformers. And currently in language models, the most popular kind of position embeddings are so-called rotary positional embeddings, which a little bit base themselves on the idea of periodicity of sines and cosines, but they basically take inspiration from a linearly polarized wave that you send through a quarter wave plate and gets circularly polarized. So this is what language models currently, as of today, use most, but of course this will change as of in a few months or maybe in a few years. This is not necessarily a time invariant thing. People will discover better positional embeddings. Okay, but in any case, I mean, it doesn't matter which positional embedding you use. You need kind of some positional information to break the symmetry, the permutation invariance that the transformer has. Okay. Good. Now we have just one more thing to add to our transformer layer, and then we're finished. Namely, with the transformer layer, we have other things to discuss, namely the residual connection. This residual connection is basically an identity mapping that we apply to each sublayer of this transformer. We have the self-attention sublayer, and here we say that the output of the self-attention sublayer to the output delta x of the self-attention sublayer, we will add x. Yeah, so x is the input to the self-attention sublayer, and the same to our feed-forward neural network. And you might ask, why do we want to implement this identity mapping? Well, I don't know if you know about ResNets, but it's exactly the same idea. So the idea here of residual connections is that, let's suppose here in this delta x, we are running into optimization trouble and gradients are vanishing. Then we can overcome this by going through this branch. Or another thing that helps us by preserving this information x all the time from an input to a sublayer to the output of a sublayer, we basically enable easier training and easier optimization of deeper networks. The question is, how deep do we usually train transformers? Well, depends on the size of your GPU. If you have a small GPU, 6 to 12 layers is usually what you do. But of course, you can go to 24, 48. Nobody knows exactly how many layers ChatGPT has because that's classified information. But I wouldn't expect it to be more than 100. The maximum size of a transformer that I've seen is 1,000, because there was a paper entitled Scaling Transformers to 1,000 Layers. And of course, to scale transformers to 1,000 layers, they went very deep, but then had to reduce the dimensionality, the hidden representation of the transformer very much to basically 8, because otherwise, with 512 or even more dimensions here, they would run totally out of GPU RAM. Yeah, and one thing I didn't mention is that, of course, we add these values after each sublayer, but adding is not enough. We also need to normalize, because if we keep adding vectors to another vector to another vector, we will eventually run into very large numbers. And optimizers of today work best in the range 0, 1. That's why we normalize after each residual connection. And this is it. We have now the transformer layer. And with one transformer layer, we can apply layer after layer after layer after layer. And when we're, when we decide that's enough, then we can look at these representations and hopefully solve the task at hand. And this is what we will discuss in the following slides. And here again, for reference, I have the transformer architecture layer in all its detail. Are there any questions regarding the transformer architecture? Yeah? Similar words. You would say cat and feline are similar words, and you would like them to have them close to each other in the space, right? Yeah. Well, that's basically everything you learn by massive amounts of data. So every time you will see, so what happens, and that is something that happens not from a sentence level, but by seeing sentences after sentence after sentence, basically the entire Wikipedia or the entire internet. Because once in such a large corpus, you will eventually run into the sentence, a cat sat on the mat, and a feline sat on the mat. So usually the word cat in the training corpus will be accompanied by similar words as feline does too. So during this whole representation learning, you will learn a vector or representation for cat, but because cat is always in a similar context as feline too, they will eventually learn similar representations, not identical representations, because of course there's a difference on when you use feline versus cat, but that's exactly the thing that happens at very, very, very large scale if you read trillions of tokens. Yeah, so it's really all emergence. It's nothing that really enforces that to happen. It's except of just this architecture that says that, okay, we didn't yet describe, and this is what happens in the following chapter, how exactly we produce language from it, but usually just by the fact that words that mean the same usually are keeping the same company, they will get very similar vectors during learning. Okay, and the follow-up? If it is used, well, it is kind of used in the sense that we will eventually get some representation. So I had this example of the CLS token that we will use to say whether well is a good continuation of the sentence or not. If these representations are good, then they should have some similarity and some structure with respect to well, and words that are having the same relationship with respect to well should also map into kind of that area, because otherwise this thing that we were describing here, this structuring of the embedding space doesn't emerge. But this structuring of the embedding space does emerge because it will be exactly a linear layer that we will apply to this representation to really get language and to solve tasks with it. Yeah, so this structuring is enforced. It's a little bit of magical that it happens, and it happens usually at large scales, so you cannot train on 10 sentences and hope for any structure to emerge. Okay, there was a question? So you have this, let's say, dictionary lookup table that, let me pull up the slide. Here. So this is kind of a lookup table that we usually have. So every time we see the word mother, we will map it to, because that's what we do in tokenization, we map it to 84, and 84 always maps to the same vector. And every time we see mother, we will get out this vector of our tokenizing database and will update exactly this vector. So, and that's a little bit of a problem. So for words or tokens that are encountered more frequently in the data, we will do more frequent updates than for not so well represented words in the training data. And that's why it's very much to expect that if you say talk to ChatGPT and use very plain language that it's used to, it will do much better responses because it will have better enforced representations than for really weird language that nobody uses, and where it will basically have words that are not trained very well and will not perform well. Yeah, but in the same way in which you update weights, you update these vectors as well with gradient descent. You just backprop until the very beginning. It's very much a reminding of adversarial examples, but in adversarial examples you manipulate the input with the idea to make something bad. Here we're not manipulating the input representations to make something bad, but really to improve the representations of this input. Okay, thanks for the questions. There was one. Yeah, so one answer is it doesn't work as well as you would like it to, because in the worst case scenarios, as said here, in the worst case scenario, we will split a very bad typo into individual characters. And of course, it's a more semantic, so let's say it's a more intuitive and a more semantically rich thing to have the concept of mother than to have the concept of M and build it out of O, T, H, E, R. That's a very hard task that attention then has to do. So it works, so transformers and language models work best in this, let's say, very, in this regime where words occur a lot, are trained a lot, and do not split into these weird things. And maybe you know of the question that you can ask to ChatGPT and it doesn't get it right, how many R's there are in strawberry. The reason why it cannot solve this question is not because it's stupid it's just because it's looking at text very differently from how we do. When it sees strawberry, it sees a token, it's just the word strawberry, and it doesn't even have the representation of R inside it. So it's where here is the concept of R in mother? Nowhere. So because we look at words very holistically that are common, like strawberry. We look holistically, we will not, the transformer will not have the very deep representation of the character level representation. It will not be able to count how many R's there are in there. But if we make a super bad typo and we have to split everything into individual tokens, into individual characters, then it will have this character level representation and it hopefully will be able to count the R's. But the problem is that these typos, if we have here a word that has bad typos and we have split it into characters, this character will be very much overloaded with meaning. It will bear the meaning of M. And what's the meaning of M? But you know much better what's the meaning of mother. So yes, typos are very bad. That's why if you do typos, usually per definition, the transformers work much worse. But the good thing, what happens at large, huge, enormous scales, is that you train on the entire internet, and people are very bad at writing. So there is enough training data for typos in the internet. So then eventually you will have some semantics for those bad typos too. Okay, one more question. Of course. Cool. I had a hackathon last week and we tried to implement a spell checker. It was harder than you expect. I mean, not because to catch easy typos is easy, but sometimes you don't know if it's a typo or the person you're talking to is very smart and using words that you don't know about and don't have in a dictionary or in the training data, right? So, of course, you could check typos and try to fix typos, but it's actually harder than you would expect in these edge cases of super rare words, when you don't know actually if it's a typo. I had there is this MMLU benchmark, and there's a question about biology, and there was the question about a telomere stand. And you really have to know to biology that it's not stand, which is a valid word, but it's strand, which is what would have been the case there, right? So typos are very hard to detect, and that's why we would like to train on typos to make models robust on typos, because users make typos. Okay. Maybe it is a good place to have the break now, because otherwise we will go into an entirely new chapter of language models architectures, and there's just more 4 minutes until the break. Okay, good. So let's have a break, 5 or 10 minutes? 10 minutes. So let's reconvene in 10 minutes.